Welcome to this next lecture, and we are discussing one of the most important and also exciting topic, that is the generation of rotating magnetic field. You I note that I have used the term exciting. Why it is? Let me clarify you. Suppose somebody comes to me and to average people and say that I want to produce a rotating magnetic field. If before Nikola Tesla, people would have suggested, okay, you do like this, you take a say something like cylinder, have two slots, I mean minimum thing you do, put a coil, pass some DC current, and it will produce a field in this direction. And if you keep it just like this, it will be a stationary sinusoidal field if you neglect harmonics, and then you rotate it by some external means, that is by a prime mover, and you have created a rotating magnetic field. This is north, this is south, and it will rotate. That is all. Because before Nikola Tesla, there was no concept of AC supply, it was all DC, and people would have created a rotating magnetic field by passing some DC current through the coils, and would have told that you now move it by some external means. Now, here comes Nikola Tesla, he tells, okay, that is a rotating magnetic field, no doubt, but I am now telling you an idea by which you can create a rotating field without moving anything. That is the most important point. And he told that you have a polyphase winding, and for that I need these things, that is what his requirement. On pen and paper he calculated all these things, okay, this is how you can create a rotating field. He demanded that if a balanced polyphase winding is made, mind you, 3 phase is a polyphase winding, okay, balanced 3 phase winding is there, and if you have a balanced polyphase supply, that is 3 phase suppose, and if you excite, and these coils are stationary on these slots, nothing, you do not move anything, you do not ask for any prime mover or things like that. Only thing he is asking that, okay, then you pass some balanced 3 phase currents through these 3 coils, IR, IY and IB. If you pass, then you have created a rotating magnetic field, just like this, equivalent to this, and it will move, field will move, coils are stationary. So, average people will give you this solution, but it was left to Nikola Tesla, who first told you can create a rotating field like this with the help of stationary coils. Coils need not be moved to create a rotating field. Coils may be stationary, you create that field, that is all. And you know by this time that in fact, Faraday's laws were discovered in 1830s or so, and it was a lone battle fought by Nikola Tesla, and ultimately in 1880s or so he succeeded. I mean, after a long time he started, he was telling that, okay, if AC supply is there, and not only AC supply, if balanced polyphase AC supply is available, then he can construct a much simpler motor in construction, and that was induction motor. So, to produce induction motor, he came up with all these ideas, and you know, after that it was all history. That is, It is now all 3-phase supply we are using, and we are using 75% or 70 to 75% of the motors to be induction motors. That was also his invention. So, he that is the very nice thing. I mean, to create a rotating magnetic field, you do not require any thing to be rotated. Even if coil is stationary, just pass 3-phase current, then with respect to the structure which houses the coil, the rotating field will be produced. What do I mean by that? That is, suppose you have a balanced 3-phase winding here. I will just show now like this, no point in drawing slots, this, that. Balanced 3-phase winding, suppose this fellow can be rotated, there are R, Y, B phase coils, pass 3-phase current, and suppose this fellow can be rotated also mechanically, but it is stationary now. You pass 3-phase current and a rotating field will be produced B, and you can make it rotate either this way or that way depending upon the phase sequence of the supply. That also we have discussed. So, suppose it is rotating in the clockwise direction. Now, whenever you say that something is rotating, two things must be very clearly specified. One thing is what is its speed and in which direction it is rotating. Of course, in rotation here it can be either clockwise or anti-clockwise, and the direction matter is already clear to me. It is depends upon the phase sequence of the supply. So, either clockwise or anti-clockwise you can make it move. Suppose it is moving in the clockwise direction. Now, the big question is what is the speed of this rotating field? Strength of the field we have seen it is constant. How much it is? 3 by 2 into B max. What is B max? B max is the maximum value of flux density of a particular phase when it carries I max current. Each phase carries I max current, but not simultaneously, at regular interval of 120 degree they will carry. Therefore, this is the thing. Now, what is the speed? We have seen that the speed is nothing but omega radian per second, and do not forget to write electrical. And what is omega? Omega is nothing but the supply frequency, 3-phase supply of omega. That is why the currents were omega t, cos omega t minus 120, etc. Therefore, omega is equal to 2 pi f, where f is the supply frequency in hertz. Hertz means what? In RPS. Hertz and RPS are one and the same thing, rotations per second. Okay, so, this is in RPS. Therefore, I can say the speed of the rotating field is f rotations per second, that is all, and this is electrical speed. Therefore, you take a 4-pole induction motor, 6-pole induction motor, 2-pole induction motor. If you say that the speed of the rotating field is 50 RPS electrical, that is same for all. Okay. Electrical speed is same for all. Now, but as you know, the speed, we want to talk realistic speed, that is the speed which can be measured with some mechanical means, or the mechanical speed, okay, theta by t is the speed, mechanical speed. So, what will be mechanical speed? Speed speed of what? Speed of the resultant field. So, resultant term we will not use anymore, it is understood, speed of the rotating field in mechanical RPS. What should I do with this f? With which should I multiply this? If I want to calculate mechanical speed, this is electrical speed. So, I must multiply with this factor 2 by p. And this is generally denoted by this letter ns. The significance of s I am going to tell right now, but the mechanical speed is equal to 2 f by p, where p is the number of poles in RPS. And some people write it like this, 120 f by p, so much RPM. This is one and the same thing, you must understand. So, this is the mechanical speed. Suppose you have a 2 pole winding, then the speed of the rotating field will be 50 RPS electrical. 2 pole machine, electrical, mechanical, no distinction, p equal to 2 cancels out. So, 50 RPS or 3000 RPM, multiply with 60. Similarly, if it is a 4 pole machine, electrical speed of the field in electrical rotation per second is f, but mechanical speed for a 4 pole machine will be multiply it 25 RPS, it will become 50 for 4 pole. If p equal to 4, ns which is equal to 2 f by p, and p in our country it is 50. So, 2 into 50 by 4. So, it is equal to 25 RPS mechanical speed. So, ns I will reserve for mechanical speed henceforth, mechanical speed, and 25 RPS is nothing but you multiply with 60, it is 1500 RPM. Because that speed we understand, okay, it was here, then after mechanical speed is, it is making 1500 rotations per minute, that is the meaning of that. So, when we talk about that something is moving or rotating, as I told you, two things are important: directions we know, and what is the magnitude of the speed, that is 1500 RPM or whatever it is that is there. Another important thing is that we must follow here. Suppose we say a car speed of a car is 60 kilometer per hour. We of course don't go on telling that it is with respect to a stationary observer. It is understood, okay, somebody is stationary with respect to whom it is moving. 60 RPM, a train is moving at 250 kilometer per hour, it is with respect to a stationary observer. Now, in this case, similarly, while talking about the speed of the rotating field, do not forget to mention with respect to whom, this speed you are telling 1500 with respect to whom it is moving that. This I am writing, you also write it down, this is very important, that speed 2 f by p, the mechanical speed or electrical speed, which is s, this speed is with respect to the structure which houses the winding. This is very important. What is the meaning of that? Suppose you have a balanced 3 phase winding here and it is on the rotor. This fellow can move by some external means, you can move it. Suppose you are not moving it. These coils you have energized with 3 phase supply. You know a rotating field results, okay, B resultant, and it moves, suppose in this direction with Ns. Now, this Ns is with respect to the coils or stationary structure which houses the coil. Now, what is the meaning of that? Meaning is that if somebody is sitting on the rotor, he will conclude that on this structure with respect to him it is Ns. But you note down that on this rotor I now impose another velocity, which is by mechanical means I am also turning the rotor. This body, rotor body, houses a 3 phase winding and it is energized from a 3 phase supply of frequency f. Then I know there is a rotating magnetic field of constant strength and its mechanical speed is this much, and suppose moving in the clockwise direction, that is fine. Now, on the top of it, if I move it with a speed say nr, another speed, then a stationary observer will conclude that the speed of this field is, if it is turned in the same direction, a stationary observer will say the speed of this field is Ns plus Nr. This must be understood. Similarly, if this fellow rotor is moved in the opposite direction, this way Nr, and this is your field which is moving already in Ns with respect to whom? With respect to the rotor. Then the stationary observer in this case will conclude that the field is moving with a speed Ns minus Nr. Therefore, this term is very important, that this speed is with respect to the structure which houses the winding. If the structure itself is also moving by some external means mechanically, then a stationary observer will differ. He will say, somebody sitting on this rotor, he will always say, okay, it is moving with Ns, that is fine, absolutely. But somebody outside observer standing on the feet, and suppose let us imagine he can see the lines of forces, then he will conclude that okay, that field is moving with Ns plus Nr or Ns minus Nr, depending upon whether the rotor itself is moving in the same direction or not. So, these two things must be very clearly understood, okay? And this will be often used in induction motor. Now, before I go to the induction motor, let us do some simple exercises. For example, I have a machine where there were slots on the stator. This is stator, it does not move. All around slots are there, conductors are there, 3 phase winding. Okay. This you please allow me to draw like this. Okay. It is a inner surface 3 phase winding, and I have planned to energize this by a 50 hertz source. 3 terminals will come out from these windings, 3 phase source we have connected. Consequences I am telling on, switch on the supply, and what you will see that a field pattern north south, if it is 4 pole is created, and that fellow is moving in space. Rotating field means that if it is 4 pole machine, one quarter I know north pole, another quarter south pole, another quarter north pole. If you pass DC current, okay. they will remain stationary. If you pass balanced 3 phase current, it will start moving, and at what speed it will move, that is n s to f by p, mechanical speed will be n s. Okay, it is moving, and why this term s, that also let me tell you. This in language they say this is called the synchronous speed. Speed of the rotating field when it is connected to a 3 phase supply of frequency f, it is called synchronous speed, because it is in synchronism with the supply frequency. Number of poles is machine thing, but essentially for a given machine, supply frequency decides what is the value of the synchronous speed. As I told you, if you make a table that is P and n s mechanical speed, and also suppose I make a table electrical speed n e, I will say if it is 2 pole and supply frequency is 50 hertz. This table is what memorizing, I mean, and also it is easy. 2 pole in RPM, if I write, it will be 3000 RPM. This will be also 3000 RPM electrical speed. 4 pole, it will be 1500 RPM mechanical speed, electrical speed. It will still remain 3000 RPM. Understood? 6 pole, it is 1000 RPM. You calculate from this, and this will remain 3000. So, electrical speed in electrical degree, they are all one and the same. Mechanical speeds are different. So, what I was telling, so you have connected this stator and you have energized it, and this I will indicate by some line and write that resultant field depending upon phase sequence, it is moving, and it is moving with this speeds n s, direction I can decide, and suppose it is moving in the clockwise direction. So, B pattern will be moving, that is all. Now, what I do in the rotor, I have a coil, and rotor is stationary, rotor, I will not run it, it is stationary. Stator is a coil, nothing is moving in this scenario, in this case, and you create a rotating magnetic field. Now, as this rotating magnetic field is existing, therefore, there is bound to be induced voltage here in the coils, because flux linkage or each conductor comes under north pole, south pole, BLV is there, all these things we now know. Now, the question is, what will be the magnitude of the voltage I want to calculate in this rotor coils? You know, the magnitude of the voltage in a coil is RMS value of the voltage is root 2 pi p by 2 into n, root 2 pi phi and kW into n, because these windings, these coils may be distributed, I do not know. Suppose a single phase coil, distributed coil, it is stationary. So, I want to calculate what will be the induced voltage because of this B. Then what should I do? I will ask what is the number of turns of this, what is its Kd, what is its Kp, Kw you calculate. Then what is this phi? Phi is the flux per pole. So, for this stator field, what is the flux per pole? That also I can calculate if it is a p polar machine, and if the peak of this B is B max. So, 4 by P B max Lr I will calculate. That is how it is to be calculated, flux per pole produced by the stator, and this coil is open circuited. I want to know what is the induced voltage generated. There is induced voltage across any coil if it has a relative velocity with respect to some field, and here this coil is stationary, this fellow is moving. In this case, there is nothing mechanically moving. So, 3 phase supply, rotating magnetic field, coils are stationary. This fellow is also stationary, I have not allowed it to move, it is held. Therefore, flux linkage changes, there is supposed to be induced voltage, and what will be the induced voltage? We have found out earlier, root 2 pi f phi k w n. Now, what is this n? This n is the relative speed, mechanical relative speed between this and this. If this is stationary, this is n s, mechanical speed, therefore, relative speed is n s minus 0, that will be the relative speed. But in this expression, I must convert it to electrical. So, it will be root 2 pi p by 2 n s phi k w n. What is n? N is the number of turns. K w n is sometimes called the effective number of turns, because of the distribution and pitch factor of the coil, this actual number of turns is reduced. That way also people think, or take the physically count the number of turns, multiply with k w. Phi is the flux per pole because of B s. Therefore, I will be in a position to calculate induced voltage in a coil. On the top of it, if I say, if this rotor is also moving in the same direction, and with respect to stationary observer says the speed of the field is n s, speed of the rotor is n r, all are mechanical speed, it is moving. That is what a stationary observer conclude, and he wants to calculate what will be the induced voltage, he wants to know. Then what he should write, root 2 pi this thing which will cause this voltage is the relative speed. If they are moving in the same direction, it should be p by 2 n s minus n r, this is this term, flux per pole k w into n. If suppose this rotor is rotated in the opposite direction as that of the field, then the magnitude of the voltage will be root 2 pi p by 2 n s plus n r. That is, calculate the relative speed between this and the field. Where the coil is there, coil sees what? If the field is moving in the opposite direction as the rotor rotation, then relative speed is high. So, you would expect higher voltage to be induced, is not. Therefore, these are the things you please go through it very carefully, and always remember, while specifying the speed of a rotating magnetic field, it is a good practice to always write down, okay, this is with respect to this fellow or that. In general, the speed of the rotating field depends upon supply frequency, which is 2 f by p, and it is with respect to the structure which houses the winding. Thank you so much. This is important lecture. Please go through it.